Alright, welcome back to time series analysis course, and today I'm going to talk about uh, multi-dimensional data, means basic or multivariable data. So if you in fact you will face a situation where you will see that you are jointly measuring multiple variables or multiple parameters of the problems over time points. So as we have noticed that last time when we were talking about the autocovariance and autocorrelation, we were talking about the autocorrelation between certain oscillation index and the recruitment series. So there were two variables that were collected at measured exactly at the same time points, and then you want to see whether they are moving together, or if there are trend effect, if there is seasonality effect, and if there is any effect beyond trend and seasonality. Now that we discussed last lecture. In this lecture, what we will do, we will try to create a abstract framework where any time series, multivariate time series will fit into this abstract framework. So effectively, instead of two time series, now imagine you have p time series or p variables you are measuring at time point t, each time point t, each time you are measuring all the variables. Okay, so you have x1, x2, xp, so p variables. Okay, p variables you are measuring at time point t. Now t runs from 1 to n, obviously. So at time point t you have a p cross 1 column vector. Okay, and capital XT is the column vector of or effectively I've written it as a transpose. So it will be like, you can think of like this, or typical in a matrix. If you read this typically in a Excel kind of format, typically it will come like one row will be your one observations. Generally that's how people collect the data. Now for the stationary series, if you assume that entire all p vectors, all p variables are stationary time series, then you can simply assume expectation of xt is mu, the mu vector. So mu is between mu1, mu2, mu p, and p cross p autocovariance matrix. Okay, so which is essentially xi t plus actually it should be x, not xi, it should be x. I will correct it. It should be xt plus h minus mu times xt minus mu transpose. This where matrix gamma h are the cross covariance function, and gamma ijh you can define as the autocovariance between ith time series and the jth time series. Okay, you don't have now a single autocovariance, since you have a p series, each of them with have their corresponding autocovariance. So for each lag you will get a p cross p autocovariance matrix. Okay, and if it is stationary, then gamma ijh and gamma ij minus h, this symmetry will hold if it is autocovariance stationary. So naturally, how you estimate sample, you use the same idea of sample moments idea. Okay. Obviously, one is a likelihood method, but in a high dimension, you have to estimate too many too many parameters. So sample autocovariance matrix works reasonably well. Uh, it has at least the statistical consistency property, typically for the stationary series. And if n, the number of sample, is reasonably larger than p, it is somewhat reliable estimator. So you can use a sample autocovariance matrix as the measure of autocovariance matrix for the p-dimensional time series. Now here I am trying to present a visual understanding of what is happening here. On this graph, on the left panel, what I have presented here on the x-axis, lag SOI minus 1, means 1 lag behind, and this on the y-axis I presented the SOI itself. So this, we have a positive correlation. We can completely see with the correlation 0.604. Now you look into this plot on the right panel. On the x-axis I am presenting lag SOI minus 6, means 6 lag SOI, and on the y-axis I am plotting the SOI itself, and what I am seeing, there is a negative, not so strong, but some sort of a negative relationship with negative 0.187. Okay. Now soil surface temperature is, this example is another interesting example where two-dimensional temperature series x S1 and S2 is indexed by row number S1 and column number S2 represent the 64 cross 36 spatial grid set out on an agricultural field. So you take a agricultural field, they have taken an agricultural field. Now you can take that agricultural field and sort of create a grid. Sorry. In that grid, each grid you measure the temperature. Okay. It's very jittery. It's extremely jittery, but it is somewhere in the range of 6 to 10. I believe it is in. The experiment was in the Western Hemisphere, in somewhere, probably in a slightly colder day. So if it is in Celsius, because if it is in Fahrenheit, it will be if it is in Fahrenheit, it is a sub-freezing temperature. So my guess is maybe it's a Celsius. I'll check it out in the data description. Now what you do, you take one row or take one column, like you just take the slice of the grid. In that, along that grid, you take the average and over time and see what series you are getting. So row average of two-dimensional soil temperature profile. So over the time period, and this is average time period, average temperature. So it's like you have taken the average over one particular grid, like one particular row kind of thing. So obviously you can have 36 such time series. You can have 36 such time series. This is one such time series. The autocovariance function now I'll talk about. So now essentially this is just whatever we have done last week. I'm just writing it in the matrix notation, because when you are handling with multivariate data, it is better to represent it in using a matrix notation. So the autocovariance function will, I've just written the autocovariance function, now become an autocovariance matrix function effectively. Remember that each H you have a matrix. You don't have a one particular value, but you have a matrix. Okay, so this autocovariance matrix function of H, you can write it in this way as usual. Just instead of vector, these are all now matrix. And two-dimensional temperature case, what you will have is gamma H is H1, H2 for two different lag, S1 plus H1, S2 plus H2 minus mu, and then S1, S1 minus mu, and then take the covariance matrix. So that will give you the, obviously now for different H1 and H2 choices, it will give you the matrix that you are looking for. Similarly, you can compute the autocorrelation matrix by dividing the variance function by taking the 0, 0, lag 0, 0 from the autocovariance function. That will give you the variance, and you divide that autocovariance function, autocovariance value by the variance value. It will give you the autocorrelation value for H1, H2 for a two-dimensional series. Easiest way to calculate 2D ACF in R is by using Fourier transform, and the detail of FFT will be covered in later in the course, but effectively that is the easiest way, and we will do that only. So we will not go into the detail of fast Fourier transform and all these things. So here is the piece of code that I'm just showing you. In the later, when we will do the hands-on, we will run this code and we will see. Essentially there is a function, built-in function in R called FFT, fast Fourier transform. So you just call that, and then the soil temperature data, I just subtracted the mean of that so that it's a location shift, and then apply the FFT, and then you just take the modulo of the fast Fourier transform, because fast Fourier transform what will give you a bunch of complex numbers, and we don't, and then from that complex number we want to estimate the modulo of the complex number. Once we calculate the modulo of the complex number, that gives us something, and then if you take the modulo will give you the complex number, and then you take the real part of that complex number, that will give you the CS, which is a covariance, stationary covariance value, and if you divide that by the CS11, that will give you the correlation values. And then if you plot them, so you will get something like this, the autocorrelation function. But now autocorrelation function is not a unit function, but it's a space, it's a surface. So it is, autocorrelation function is now become a surface, autocorrelation surface. and clearly at 0 0 there is a huge spike which is nothing but 1 with itself, and then you can see that there are some periodicity. We can clearly see that there is some periodicity. We can see in this direction, in the row lag direction, clearly there is some periodicity we can see. On the column direction we don't see much of a periodicity. So this is an important thing. So when you have a multivariate data, multivariate time series, which direction you are getting your periodicity is very important. Okay, so identifying the correct direction of the periodicity, whether it's a row side, whether it's a column side, this is for 2 dimension. Then the problem is more than 2 dimension we can't even plot. In 2 dimension at least I can plot and I can identify, okay, I am getting the periodicity on the row direction. Because if you look into the original data set, almost impossible to make any sense out of it in which direction you have the periodicity. But when you finally look into the ACF plot, clearly it looks like on the row direction you have the periodicity and column direction you don't have the periodicity. The periodicity is not column direction, it is on the row direction. Now question is obviously how we extend that to the higher dimension. That's a difficult task. Now I will move on to the next topic called time series regression, because this is very important topic. From here on, the built on the time series regression, I will move on to the ARMA, ARIMA and SARIMA models, because these are the, particularly ARIMA and SARIMA, these are the 2 models which effectively would become a bread and butter for you guys who wants to be a data scientist or whatever, statistician, data scientist, whatever you call yourself. Whenever you have a time series, typical classical time series, ARIMA and SARIMA type model works very, very well. So let us start with the understanding the time series regression first, and that will become our foundation and block, and from there we will move on. So now XT is a dependent time series, and ZT, ZT1, ZT2, ZTQ at the same time points. So essentially you can think of, you have a data set of dimension Q plus 1, right? Your response series is XT. At tth time point you have small xt. This is capital XT. Capital X means XT1, XT2, XTK. So, or in this way, or X1, X2, Xn. Sorry, here I'm just taking it as a T. And ZT is effectively, X can be matrix also, vector also. Let's not complicate. Let's take it as a univariate time series. Think of X as a univariate time series. Z is a q-variate input vector, also measured at exactly time point t. You have that, right? And we consider it as an input. This input is fixed and known. Not necessarily always it will be fixed and known. It could be stochastic also. For the time being, you consider it as a fixed and known. And then you can set it up as a xt equal to zt transpose beta plus omega t. Omega t is ID random noise with mean 0 and variance sigma w square. Now you can ask me, why am I using a different notation from my regression classification courses? Because I'm following Shumway-Stouffer book, so that if you follow that book, at least you have a chronologically, you will not have difficulty understanding the whole flow of the lectures. Okay. Now obviously OLS, you can use OLS regression solution X, which is Z transpose Z inverse Z transpose X, and you can simply apply LM in R, and that will give you the just simply air passenger as a function of time. Okay, if you do that, which will fit you a simple model beta naught plus beta 1 T. Now this will give you almost 85% accuracy. This will give you a straight line fit, which is great and not so great. Then obviously you want one more engineering feature or Fourier feature, which is sine omega t. Omega we have taken 2 pi I, 2 pi, and then if you fit that, it started picking up some seasonality. And then if you put beta 1, beta 2, sine omega t, cos omega t, and all these, more and more term you start putting up, then it start mimicking the periodicity, and you can then you can keep doing it as much as you want, and eventually you may end up with a very overfitted model. So certainly you want to avoid that. So what you do, you either apply a stepwise feature selection technique or some kind of lasso feature selection technique. So here is my one question: can you apply elastic net here? Do you remember what is elastic net? So two questions. One is, can we apply it? And second question, do we need to apply it? Think about it and come back to me next week. So after fitting the model, we get a fitting like that. You can see that after I did a stepwise selection, and after stepwise selection all the cost terms were dropped. So the cost 2 term, cost 1 and 2 terms were there, and then after that only the sine term was there and all the cost terms were dropped. So some degree of model selection is probably a good thing. So the simple linear regression model with trend and seasonality, that is what you should try first. Okay, and then trend and seasonality can be modeled as a feature engineering and or variable transformation, whatever you call it. Then after that, what you can do, you can look into the residuals. Now once you get the residuals, what you can do, you can check whether they are IID or not. This is what we are going to do once we if they are not IID, so if the residuals are not IID, so that means there are still certain information left in the residual, which or signal is still left, which are not modeled by simple trend and seasonality. Okay, that residual are typically called detrended time series. In industry, they don't like to, we call it, in academia we call it residual. In industry they don't like to call it residual, they generally call it detrended time series. It took a while for me to understand what they were talking about, but when they explained me what they were talking about, I knew what exactly they were doing. But basically, now you have this residual series or the degenerate time series, now which will be a stationary. You can see that these are the mean stationary. Sometimes it is even a variance stationary, but they are autocorrelated. Now what you can do, you can apply ARMA or ARIMA type model on those kind of time series and push your forecast from 95% to 98-99% in the out of the sample. So ARMA ARIMA in this kind of, even in this kind of model, ARMA ARIMA can give you a really big push to improve, because in this model you will not be able to go beyond 95%. Okay, when you have a very strong 90, like trend and seasonality, but even after that you may have some residual which are autocorrelated, which are local in nature. ARMA, ARIMA, SARIMA type models are very good in modeling the local behavior. They are not good in, not necessarily, sometimes they're also good, but not necessarily they will be, ARMA, particularly ARMA and ARIMA, not good in picking up the trend. In order to solve that issue, the SARIMA was developed, and SARIMA is very good with picking up the trend and seasonality and all. So sort of a SARIMA is the most state-of-the-art model when it comes to regular time series model, and we will talk about it in the next 5, 6, 7 lectures. We will be only talking about these things. Okay, so let us continue. I'll move to the next notes. So here is let us start with an example to understand the problem a little bit more. Pollution, temperature and mortality. So this is a data about a decade, over a decade, monthly data in the Los Angeles, one of the county in the Los Angeles County. So cardiovascular mortality, the black series is the cardiovascular mortality rate. Okay, the red is the temperature, and green is the particles. Typically my guess is it will be either PM 2.5 or PM 10. Okay, some pollutant particles they are measuring, monthly level of. Okay, so clearly there is a periodicity. Okay, question is but that doesn't mean that one is affecting another, one is causing to move the another. Each of the series may have their own process to follow. Okay, each of the series may have their own process to follow, and they are not causal, they are not necessarily causal. So obviously this kind of data, what we try to explore, we explore the possible effect of temperature and pollution on weekly mortality in Los Angeles County. Now, as I said earlier, that there is a strong seasonal component in all of the series corresponding to winter and summer variations, and downward trend in the cardiovascular mortality over the 10-year period. If you look into carefully, initial 5 years, the rate was, when it was going up, it was going quite high, above 100. But after 1975, it is not like it has not going up, but it is going up much more less frequently. Now, so the data looks somewhat like this. So it's a weekly data. Sorry, I think I told you first it's on monthly data, but it's a weekly data. So and you can expect a 52 week frequency periodicity. Here is a scatter plot of mortality versus temperature versus particulates. So what we see that particulates and temperature, there is not much thing are happening. Temperature and mortality is negatively correlated. This is known for ages, because particularly winter temperature mortality rate goes up, because during the winter those who are vulnerable like senior citizens or children who have a low immune level, they often get sick. So in extreme cases people die. So at a lower temperature during the winter season, mortality goes up. This is true for across the world actually. So this phenomena is assuring data is somewhat reliable, and data is telling you what are you expecting. What is interesting fact is the positive relationship that we are seeing between particulates and the mortality, at least on the raw data. With the increasing particulate, we are seeing a bit of a higher mortality rate. This is an interesting feature that we are seeing. Obviously we need to detrend it, and after detrending if we still see or not. So after detrending, we can say, we can say that whatever we were seeing the relationship, it is just because of the trending effect. Okay, so, and that is a good news, because all you have to do probably reduce the particulate level to reduce the mortality rate. That's what you have to try out. Then here is the autocorrelation function for mortality. Clearly there is a periodicity. This is a yearly plot, temperature and particulates, and this is the correlation, cross correlation function between mortality and temperature. And so what kind of model that you can try? First, obviously the bare bone minimum model is mortality as a function of trend, because we have seen there is a possible declining trend. So, and then you want to put up a differencing effect on the trend. So this is the differencing effect and quadratic effect of the trend. That is what it is giving. And then after modeling everything for the trend, is there anything left which is correlated with the particulates, where the mortality is correlated with the particulates? Okay. Now, obviously, when I fit this data, I'll share the code with you guys, that it gives me a R square of 0.21, 0.38, 0.45 and 0.6, and mean square error out of the mean sample, mean square error about 79, 62, 55, 40. So mean square error dropping means also performance of the model is going increasing, right? What I have not done is I have not put any seasonality effect for the trend, so I'm leaving it for you as a homework. And see, after adding few sine and cos, after doing a stepwise selection or a lasso selection, what do you able to improve it further. Okay, I'll share the code and everything in the Moodle, also in the GitHub, so that you guys can try yourself. So here till now, whatever we were doing, there were no lagged variable was involved. Everything was t versus t, xt versus yt, or yt versus zt. So if you look into this model, there were no lagged variables. So what is t naught? T naught is basically average of the t. You take all the t values, take the average. Now tth time point minus the average, the difference time point, difference squared time point. So this kind of thing. Sorry, that is temperature. I think it was temperature. Sorry about that. So I have put a trend. So this is a t, small t is time. Yes, small t is time and capital T is temperature. Sorry about that. So T naught is the average of all the temperature. So it just you're doing a location shift of your temperature data. No, it is not going to disturb your analysis. Only thing is it's the convergence, model convergence, beta naught and beta 2, these coefficient will be much prominent instead of taking a very small value or very large values. So what is not left is the modeling the trend part. It's not left, so you can try that. But everything is at t. There is no lag variable was involved, and so here we want to model the lag variables. If you want to model the lag variables, if you take the recruitment data and the Southern Oscillation Index data, so all you do RT beta naught beta 1 and then 6 months behind Southern Oscillation Index data as a covariate in your regression model. And that, even that model sort of give you 36% of the explainability in the model, or the variability of the recruitment variable can be explained by just 6 month lag Southern Oscillation Index. So this example tells us that we need to bring the lag variable in our predictive regression model. But we just cannot bring them ad hoc basis. So what we need is some tools and engineering, and in order to take so that our model become much more robust, in a sense that our abstract level we have a much more robust idea about how the model works. So we need to bring the idea of backshift operator. It is absolutely crucial, and it is beautiful importance you will realize only when you will see Sarima model. Okay, so it's one of the beautiful piece of math, I would say, that makes our life much simpler. So let us see what is the motivation of the backshift operator. It is necessary for time series data to be stationary, so that the averaging lag product over times. So we need to bring the lag variables in our models. So this is number one. Within time series data, it is the dependence between the values of the time series that is important to measure. So again, same point, at least must be able to estimate the autocorrelation with certain precision. So it would be difficult to measure the dependence if the dependence structure is not regular or is changing at every time point. So basically non-stationarity it is talking about. To achieve it meaningful statistical analysis of time series data, this is one of the important thing. It is crucial that the mean and the autocovariance function, so mean function and the autocovariance function, satisfy the conditions of the stationarity. Okay, often this is not the case, as we have seen so far. Quite a number of examples, including the air passenger data, they were all non-stationary series. Now, easiest form of the non-stationary to work with the trained stationary. Okay, what is trained stationary? So basically, it is a model which has a stationarity around a trained, you have a stationarity. Okay, then your life is much simpler. What does it mean by that? So you have a xt which is a yt, mu t plus yt, where xt is the actual observation. Xt is the actual observation, mu t denotes the trend, and yt is a stationary process. Okay. Now, what you can do, you fit a trend line. You know what is mu t hat is a fitted trend line. Now you subtract xt minus mu t hat. What you get? Yt hat. Yt hat is your stationary process. Now you can do the analysis on the yt process. Okay, so that is precisely what I was trying to say, that in the air passenger data, if you fit a trend line, you fit a seasonality, after doing all the hullabulla, you reach up to 95%, and you have some residuals which are still autocorrelated. You can take the residuals, you can check the autocorrelation, you will see the autocorrelation, significant autocorrelation. Okay, this is precisely I was talking about, that you have basically at least you have a mean stationary process in the residuals after taking care of the trend and seasonality. And you may have autocorrelation, no problem, and all you assuming that your autocorrelation is stationary. That's it. That is the assumption that you are making. So here is the chicken price data set that is again available in the TSA data set that comes with the book. So again, what we are thinking, like, okay, xt is the price process, which has a mu t, a trend, plus a yt, a residual, which is a stationary process. Now mu t is a straight line, sort of beta naught plus beta 1 times t. So you fit that model, and that itself explains 91% of your explainability. But still, and now you take the residuals and plot them. Understand what I'm saying? All you have to do, fit the model, you get the beta naught beta 1, you can fit it using LM, get the fitted values. Once you get the fitted values, subtract that from the observed values, what you get the residual process. Plot that residual process, this is what you will get. Now this is a definitely mean stationary process. It might have a strong autocorrelation, but it is a mean stationary process. Now, so this is what I have just explained it. Mu t hat, you just plug it in those numbers, and y t hat is something nothing but xt minus whatever mu t hat you have. That will give you the y t hat. So we have discussed all these things. Yeah. Now this is the, so this was the series that we discussed, and then this is the autocorrelation function of the series. So clearly some of the auto lag values are statistically significant relationship, negative relationship, but there is a which we cannot ignore. Okay, and obviously those lag values you can now think of bringing them in your model. So your model will be like yt equal to beta naught plus beta 1 times t plus gamma 1 times y t minus 6 or t minus 10, something like that. Okay, and then obviously plus some residual. So essentially you can keep trying that as long as you have a, when you achieve a white noise, then you know that okay, you have nothing left, everything, whatever your series had, you modeled everything. But here, after modeling the trend, what you have is a residual, and residual has autocorrelation function. So that means still there are some signal left in your data which you are not using to enhance the predictive power of your forecasting model. So autocorrelation function is clearly telling me that maybe lag 7, lag 8, one of the lag is strong enough, or maybe lag 2 is strong enough to bring them, these lag variable, bring them on the on your model. Okay, now how you do that, that's a bit of a trick that we need to work on, because you don't want to, remember that this is the autocorrelation function on the residual, not the data itself, not the series itself. You understand what I'm saying? So you have to be careful about that. So you cannot just take the, okay, let me just take yt minus 6 and put it as a predictor in the model. All you know, they are non-stationary process. Your all estimation model may become non-stationary, and everything will be completely out of the window. So you have to be very careful about that. So you can keep trying that. You can keep, if you can try that, you can try that. You can try that. But now I'm going to introduce a completely different idea. Instead of working with the series itself, can we work with the difference of the series? Now you look at the original series. So original series looks like this. XT looks like this. This is my original series. Now if I take the first difference of the original series, just consecutive difference, basically xt minus 1, that gives me delta t. Plot delta t, what you get immediately a complete mean stationary process. Now, if I build my entire model based on the mean stationary process, I know at least my current data, the data I'm handling are all stationary process. Obviously, I want to do forecast for time 3, 4, 5 ahead, but at least I know my parameter estimation, everything will be much more stable, consistent, and reliable parameter estimates I will get. And I can then use that structure to develop a new model. Let us see now what is the ACF plot of this series. ACF plot shows a very interesting, its ACF plot itself behaves like a sinusoidal curve. You can see that ACF plot itself is behaving like a sinusoidal curve. So actually the series is much more complex than what we thought. If you see, if we didn't expect, it was a very blunt series, right? It was an extremely blunt series, but when we took the first difference and looking at the autocorrelation plot, it's a completely different ball game. So now the question, so we want to build our model, forecast model. What we realized that non-stationary data, in non-stationary time series, my parameters are changing every time point. So if my parameters are changing at every time point in a non-stationary data, I cannot use my usual, estimation methods of parameter estimation method or model learning method, because remember that my all tools and techniques are based on at least stationary assumptions, if not independence. So now what to do? So you have two approach. Now I have presented you. One is either you detrend the series, fit a trend line, fit a seasonality line, and get the trend, get the residuals. Most likely residual will itself a mean stationary, at least a mean stationary process, and you hope that correlation structure will also stationary, autocorrelation structure. Or you apply differencing technique. You take the consecutive differences, and if you see that consecutive differences are mean stationary, immediately just plot the data. You can, if you don't want to plot the data, you want to automate the process for an industry, you can do a test for mean stationary. If it passes, you will go to the next level, right? So either you can work with the detrending data, detrended residual, or you can work with the differencing method. So one of the disadvantages, differencing does not yield an estimate of the residual stationary process. So I cannot get the residual process. So that means that process, that technique, that methodology will be completely different methodology. If you want to go through that, either you can go through the detrending route or you can go through the differencing route. If an estimate of YT is essential for you, then detrending may be an appropriate process for you. But if your goal is to coerce your data to stationarity and build a good forecasting model, then you can go for the differencing method. If you not that much care about the residual method, then you can go for the differencing method. Now, differencing is also a viable tool if you have if the trend is fixed. So your mu t is beta naught plus beta 1 t. Now if you take xt minus 1, that is mu t plus yt minus mu t minus 1 plus yt. Now you plug the beta naught plus beta 1 t in cases of mu t and mu t minus 1. So what you got here beta naught plus beta 1 t plus yt minus beta naught plus beta 1 t minus 1 plus yt minus 1. In the process you lost beta naught, one parameter get reduced. You don't need to estimate beta naught. You left with beta 1, and what you got is beta 1 plus yt minus 1. If you remember your differential equation class, that you have the d of yt equal to alpha plus beta t, then if you take the difference a line with the thing, then what you left with is the beta 1, right? So here you just left with the beta 1 and a bit of a noise. Because differencing is going to play a central role in the time series analysis, so it receives its own notation. Okay, so xt minus 1 get this inverted pyramid notation xt, and this notation is called nabla. Okay, and in general mathematical sciences, it calls nabla. It's a Greek notation, ancient Greek notation. That's what I have heard. In statistics, this nabla notation is known as backshift operator. So if you see nabla xt or the backshift operator xt, that means it is nothing but xt minus 1. In the backshift operator, immediately what happens that the first difference eliminates the linear trend. As soon as you apply the first difference, if there is a linear trend, it will be eliminated. The second difference, now you got a unit series, right? Nabla xt. You apply again backshift operator or the difference, another difference on the first difference. The second difference will eliminate the quadratic trend, and so on. Does it make sense? Anybody in doubt? So all you have to do is you have the xt in the column. Second column you create is take the consecutive differences. You create a column, right? That is your first difference. Now you create a second column. You take the consecutive difference of the first consecutive differences. That will be the second backshift or second differences. So you can keep doing that. So you are not taking the lag. Remember that you are not taking the lag. You are taking the differences, consecutive differences. Okay. So it's applying is very simple. Application point of view, it's very simple. It's not a very difficult thing to do. In fact, you can write a function of your own backshift operator in 3 lines. Okay, so we will see that. So we define backshift operator by bxt equal to xt minus 1. And extend its power. So b2 xt is, you can write it as a b into within bracket b of xt minus 1 equal to b of xt minus 1, because b of xt minus 1 is xt minus 1, sorry, this will be xt minus 2. It should be xt, and then it should be xt, and then it should be xt minus 1, and then it should be xt minus 2. Sorry about that. I will make the correction when I will share it with you, and so on. So you can define bk xt equal to xt minus k. So previous one was a difference operator effectively, or backshift operator, and this is backshift operator. Okay. Now obviously these information, like if you take b inverse b, that will give you 1 xt. You can write it as a b inverse b xt, and b inverse xt minus 1 will give you back the xt. So the b inverse will call it as forward shift operator. Okay. Now nabla xt, which is xt minus xt minus 1, you can write it as a xt minus b of xt. Now you can take xt common, you can write it as a 1 minus b of xt. The second difference is delta 2 xt, or nabla 2 xt. You can write it as a 1 minus b square xt, because from here you can say nabla is equal to 1 minus b. Okay. Simple algebra, all your basic algebra, just walk through, like your college algebra, simple, your bachelor's first year algebra will just walk through here. And this is the power of backshift operator. It's very simple, don't like nothing new. Okay, so now you nabla 1 equal to 1, you can treat nabla as 1 by b 1 minus b, so nabla square is 1 minus b square xt. Now you apply 1 a minus b whole square formula, 1 minus 2b plus b square xt. Now you break it up, so what you have, xt 2 minus 2b xt plus b square xt, and then 2bxt is 2xt minus 1, b square xt is xt minus 2. So essentially the same series, it's give you different kinds of operations. It's completely open up. These algebraic operations, simple algebraic operations, is open up lots of different model combinations for me. We wouldn't have even thought of this kind of combinations that we could have tried. Just simple nabla operation, 2 operation, it gives me a simple, so many combinations, permutations and combinations of model operations we didn't even thought of. Okay. So this is a homework for you. I'm giving up. And now, obviously now I can generalize it to the D difference. One more minute and we'll stop in this slide and we'll continue on Thursday. Difference of order D is defined as simply nabla D equal to 1 minus b of b to the power d, where we may expand the operator 1 minus b to the power d algebraically to evaluate the integer value of the t. So you can effectively expand it just like your Taylor series expansion, kind of series expansion, and use that to your advantage to get the optimal solution for your model combinations. Okay, so we'll continue on this path and to build our, obviously first ARMA model, then ARIMA model, and then finally seasonal ARIMA or SARIMA model. Okay, so all right, so let's continue on Thursday. Today I'll not be able to continue, my throat is all choked. Thank you very much.